Hi, everyone. We are the University of California, Los Angeles Steel Bridge team, and this is our video presentation for the 2021 SSBC Supplemental Competition. I'd first like to start off by introducing our team. My name is Alexis, and along with Stacy, we are the project managers. Our design team is led by Catherine and Joseph. Our analysis team is led by Sam and Aaron, and our construction team led by Riley. This video will be broken up into a couple of different sections, starting off with a short introduction, followed by a discussion of our design procedures, analysis of the bridge, construction sequencing, and finally a conclusion overview. We think that our bridge would be a great fit for the Missouri-Katy Trail State Park as a solution to the historic flooding that leaves portions of the park inaccessible. Our 1 to 10 scale model of the bridge takes into account factors such as strength, stability, weight, constructability, and aesthetics, which we believe will make the bridge a great fit for the job. Overall, we estimate that structural costs will be roughly $1,645,000. Construction costs will be roughly $2,263,000, leading to a grand total of roughly $3,881,000.
Here are the drawings for our final design. The bridge envelope is drawn in as well for reference. To meet these constraints, the bridge is approximately 22 feet by 4 feet by 4 feet and feature 1.5 foot offset piers on either side. In the section view, the template is highlighted and the bridge width and the stringers provided with the proper clearance throughout the span. During construction, the cores are divided into 7 sections of approximately 2 feet and 10 inches to fit within the box specified by section 8.2.2.2. The arch is divided in a similar fashion. During the design process, the bridge aims to maximize structural integrity while also minimizing costs in terms of weight and construction time. The first decision was between an arch and a deck. Although both designs have their advantages, the guiding principle was that an increased height would lead to increased stability and minimal deflection. While the deck bridge weighs less and requires less assembly, the additional stability an arch provided was what allowed us to select it. In terms of core design, our cores are composed of 3 1-inch square tubes arranged into triangles and connected by thin webbing. Using the same principle as with the arch and the deck, these triangles were eventually rotated to have a height of 6 inches. This decreased vertical deflection substantially without compromising lateral structural integrity and also optimizing cost.
When designing the connections, there was an emphasis on maximizing the ease of constructability while minimizing the forces on individual members. All 3 connections were modeled in SolidWorks to help visualize how they would fit together. We used tube and tubes in our arch to add stability and stiffness. They are also easy to construct because you can rotate the pieces and align the bolt holes. Plate-on plates were used in the deck to help assist deflection. In the cord legs, we utilized T-slots because the legs only experience downward forces. Through optimizing the structural cost equation, we found that designing a heavier bridge was favorable because the deflection penalties were greater than the weight penalties. Mainly load cases 3 and 4 were analyzed because they were the extreme of the deflection values. And with that, our final structural cost came out to $1,645,512.50.
We use SOP 2000 for our structural analysis program to check the deflections and loads on our bridge. Our model assumes that we will have ideal fixed and pin connections, and here's a figure to show which connections are fixed, which are the squares, and which are pin, which are the circles. However, in reality, the connections that we use don't have strict fixed or pin behavior, so we end up having a combination of the 2 behaviors. Our model also assumes that we have ideal members and doesn't take into account things like manufacturing errors and general wear and tear, so therefore deflection in real life would be higher than what the model projects. Here is an animation in SOP 2000 of our bridge undergoing loading.
Here's a table listing the predicted sway and vertical deflections under the 6 vertical load cases and the predicted lateral deflection under the 6 lateral load cases. Note that the max sway of about 0.07 inches occurs under load case 6, whereas the max vertical deflections of 1/5 of an inch occur under load case 3. All the predicted deflections are much less than the max allowable deflections for this project, thus leaving room for a factor of safety.
For our design checks, we analyzed a deck member for both shear and moment capacity. For both, the nominal was greater than the ultimate anticipated load, so therefore the deck is able to withstand the projected loads. For local stability, we looked at one of the arch members because they will be subject to compression. The circular 1 inch by 1/16 inch section is considered compact, so local buckling does not apply. For flexural buckling, the nominal compressive strength is around 12.26 kips. The model shows that a maximum of 1.6 kips will be in compression and acting on the member. So therefore, the arch will not fail due to flexural buckling.
As part of our model verification, we also created a free body diagram of the north stringer of the bridge under load case 4. We assumed that the most important loads to consider were the loads applied for the load case, the reaction forces from the truss diagonals, the reaction forces from the legs, and the self-weight of the stringer. The reaction forces between the arch diagonals and the stringer were found by simplifying the bridge as a truss due to the degree of static indeterminacy in the bridge. This free body diagram was then used to calculate internal shear and moment along the stringer. As our stringer represents 3 different chords that are connected by webbing, it's difficult to compare exact values to the model. However, we found matching patterns in the SAP model and hand calculations, such as discontinuities in shear where the truss diagonals attached to the deck, as well as peaks in magnitude of internal shear and moment where the load cases were applied.
The construction cost is calculated by multiplying the construction time by the number of builders and 70,000, assuming no penalties. In order to decrease the construction cost, we must reduce the construction time by the number of builders. To approximate the construction cost, a mathematical model can be created based on the assembly time per part, transportation time, and the number of builders on each side. To reduce the construction time, the bridge is built the most efficient way possible. The build starts on one side of the deck, starting from the legs, and each side builds towards each other using the deck cords. Once the first side is done, one builder on the right holds the deck to prevent it from falling while the other builders make the second side. After both sides are made, the 2 end laterals are connected to allow the bridge to stand on its own. The same approach is used with the arch. Each side builds from the legs towards each other using the arch cords. Once one side is done, one of the builders from the right holds the side to prevent it from falling while the second side is built. Once the arch cords are built, all the arch laterals are put into place, followed by the arch diagonals. Then it's finished by putting in the deck laterals. This method reduces the amount of downtime any builder has and ensures everyone is moving as efficiently as possible. When considering the different building procedures, the most important decision is between 4 or 5 builders. The 4 builders reduce the cost of people but sacrifices construction time, while the 5 builders does the opposite. We can use the mathematical model to compare the 2 setups, and when calculated at different assembly per part times, it's clear the 5-person setup is cheaper. This is because the bridge is unevenly split, about 1/3 of the parts being on the left and 2/3 being on the right. Because of this, the right has to do twice as much work as the left, and the left often finishes construction of their part before the right and has to wait for them to catch up. By adding a 3rd builder on the right, they're able to keep up with the left better, reducing the time by 5 minutes. With the assembly process and 5 builders, the approximate construction cost is $2.2 million.
The total projected cost of our bridge is around $3,800,000. A little less than $1,650,000 will be due to the structural cost of the weight and deflection of our bridge. Around $2,200,000 is due to the construction cost. Thank you to our project advisors for all of their help, and thank you for watching.